Okay, assalamualaikum and a good afternoon. So, welcome back to this week's lecture. Uh, so today, let me go into the essentially the new chapter of Boas. So, let me share my screen. Okay, I hope you are seeing my screen. Yes, so okay, let me go to the notes and we'll start the lecture now. So, okay, essentially we are going to look at matrices as part of our linear algebra chapter. So I think I've already started doing something on it. So let me go down. Okay, so essentially matrices are also part of linear algebra simply because two basic operations that we have mentioned before. Okay, essentially we have vector addition and also scalar multiplication, which you recognize these are parts operations on what we call spaces. So I would not essentially this topic can be approached in many different ways. I'll probably introduce something slightly different from what Boas did, but more or less whatever Boas covers, I will try to cover everything. But maybe I'll do something a little bit more to actually give you some insights on these topics. So that one of the things that I already mentioned before, the operations that you have used for the case of vectors, and vectors have been written in terms of components in this way. So this is already a matrix. Okay, so vectors as 3 by 1 matrix. This is for 3 dimensions. Okay, so one could easily generalize this to higher dimensions. So here you have just your x, y, z component. So you have your vector addition here. Okay, so you add two vectors, v plus w, you always get another object, which is essentially the same kind of object as the two initial objects. And this, the other thing is scalar multiplication. It's another operation. Okay. Something going on. Please let me know if I've got disconnected or somehow being interrupted in any way. Okay, so let me know if there's something happening. Okay, by voicing it out because I cannot see you. Okay, so so these two are parts of what we call linear operations of linear space. Linear space is just another name for vector spaces. So this is roughly vector space. And vectors, you often limit yourself to this kind of objects with 3 components or higher if you want. Okay, but generally all types of matrices that you know, so now we go to the general case, all the matrices that you know which are say m by n matrix, meaning you have m rows, so here are m rows. Okay, so this is m rows and n columns, so let me write here n columns. So So in other words, your matrices are just arrays of numbers, but really, if one try to do this properly, it's not just a arbitrary array of numbers to be behaving in a certain way. One of the ways that it's been needed that you can define what we call the addition of two matrices. So the addition of two matrices, then you have to add the same type of matrices together. So it's m by n over here, then you add another m by n matrix. You cannot add two different types of matrices. Okay, so you have to have the same type, and then the resultant is this m by n matrix. Okay, so this is just an analog of the original vector addition. Okay, over here, so you have 3 by 1 matrix, you add another 3 by 1 matrix, you get another 3 by 1 matrix. Okay, so in this particular case, you have the same thing, same procedure, same operation. You have an n by n matrix added to another m by n matrix, you get another new m by n matrix. And similarly, for the case of scalar multiplication, you can define the same thing, where your scalar just multiplies all the entries inside the matrices. So yeah, these are pretty obvious. So, but what is not so, perhaps not so obvious to some people is that, so you can regard your matrices now as vectors. Why? Because you have these two operations that define your algebraic operations that you have for vectors. So in other words, how is this so? Well, one of the things that's first of all, you can see the ordinary vectors that we had earlier, which is a column matrix. So a column matrix is just a special case of that. Okay, but the other thing is the following. One could really think about the n by n matrix, rather than having written in this way. For example, just do a 3 by 2, for example. Rather than writing your entries of this matrix in this way, I could have written, for example, in this way, with 6 elements. You have 6 elements, but written in terms of a row and a column thing. But now I can write the whole thing as a single column, and you can actually do that. So the only thing that's happening over here is these two are more or less the same object in inverted commas, but you lose a kind of information over here. So one can think of say the marks of 5 different subjects for a class of 20 people. So I can write in terms of a 20 by 5 matrix. But if I start, this should be 100 rather than 150. If I start to write the 100 entries of this 20 by 5 matrix as a single column, then unless you specify which one is corresponding to which subject, you might lose information that way. Okay, so the matrix structure in this manner would be richer. This is richer. This is less rich. Okay, but again, you can actually do it if you want to. Okay, so so you can think of it as a more general vectorial object. Okay, the other thing one could actually try to do with matrices is to introduce the index notation. Okay, and this is what you call convenient, because the way you do things, for example, in the vector operation thing or the addition operation thing, you add ijth component of your matrix A with the ijth component, the corresponding ijth component, and then you get your ijth component of the new matrix. So in other words, what's important here is the position of your row and column. So the ijth index, for example, the first index corresponds to the row. I'm just making sure that I remember correctly. The second index is essentially your column. So for example, A12 is the first row, correspond to the first row, and second column. Okay. Again, this might be, I'm not sure how much you have done matrices in terms of index notation in that sense, but I think it's pretty obvious. So one can shortcut writing matrices in full by just writing it in terms of the index notation. So that is equally acceptable. But of course, sometimes if the matrix is small, for example, a 3 by 3 or even a 5 by 5 matrix, then you normally just write the whole matrix down. But you have, for example, in some computer calculation, you might have something like a 1000 times 500 matrix. Then you don't really want to write that down. Okay, so in computer programs, then you start doing it in terms of some kind of for loop, for example. Then you'll be dealing with index notation. Okay. Besides this so-called vector addition and scalar multiplication, because of the structure of the matrix is richer, as I mentioned earlier, there are some other things that can be done with matrices compared to just ordinary vectors. Okay, so one of the things that is possible to consider, for example, is the case of over here again it is going to have to be limited to a square matrix. A square matrix is what? A square matrix is where the number of rows is equal to number of columns. Okay, otherwise it's called a rectangular matrix. Okay, so in the case of the square matrices, there is a operation called the trace. The trace of a square matrix, what does it correspond to? It corresponds to just adding up the diagonal elements. So for example, here this will just correspond to A11 plus A22 plus and so on until ANN. Now, why is this so-called operation being defined at all? Is something to do with the character of the matrix itself. Probably later on when you learn about eigenvalues, then this trace of A, okay, will be related to some form of the eigenvalues. So these are going to be very important. Eigenvalues actually characterize a matrix. Okay, what else can be done with matrices that does not appear doesn't appear in general for the case of the ordinary vectors is the transpose. You can actually transpose, for example. So this is not quite true for the statement over here. I can transpose, for example, alpha, beta, gamma here. I transpose that. So this is a column vector. This is a 3 by 1 matrix. If I transpose that, so I put a notation transpose here, then it becomes a row matrix, alpha, beta, gamma. So this is 1 by 3. Okay. So it also works for the case of the vectors, but then this thing is much more general than that. The swap here you can even imagine, here you convert a column to a row. Here you sort of think of your transpose operation is swapping rows into columns and then your columns into rows. So these are, again, I believe some of you have done matrices before, and it's quite easy to understand what I'm saying. Okay, so I believe, have you done matrices in this index notation before? Maybe I should interact with the class. Yes or no? That's all I'm asking. Yes, okay, great. So I'm just, no, there are some things that I need to check on. Sometimes, no, I might be talking alone and things like that. So, okay, so in the case of this index notation, your transpose becomes, since we convert your row into a column and column into a row, then your index notation will get swapped. Okay, so I remember the first position corresponding to the row and your second position corresponding to corresponding to the column. So since column gets swapped in a row, so I have the column index over here becomes a row index, and your row index over here becomes a column index. Okay. So again, these are pretty simple things that one can actually do. And of course, now you define, okay, the first thing that we have defined is addition, and then multiplication, and then we define the transpose. So we have these three, what you call, three different operations already sort of naturally there for the case of matrices. So sometimes what you want to do is to be able to make combination of all three operations. So in this particular case, I hope the auto admit is working. So if somebody is having trouble to come in, let me know. So okay, here I'm mixing two different operations. Okay, first you have your so-called addition, and then this is followed by a transpose. Sometimes, so in other words, so here the way it's been written is like you do the addition first, followed by transpose, right? Now, sometimes you want to make sure that, okay, if I swap these two operations around, are they the same thing? So if you have swapped it around, then I should be doing transpose first, okay, followed by addition. So how do we check that? Well, the best thing to check is using the index notation. Since I can define two matrices, okay, that two matrices added together can be written in terms of index notation in this way, and the resultant matrix will be A plus B here, and then your index notation is IJ again. Okay, so I can do using that index notation to do things. Okay, so here A plus B IJ with the transpose. So what that's going to be, I will transpose the what you call the two indices there. The I becomes the J, the J becomes the I. So that's the transpose operation. And then I have the addition. So this will just become AJI plus BJI. But what's that? If I transpose this again, then this corresponds to A transpose IJ plus B transpose IJ. So in other words, doing these two in any order is the same thing, it's equivalent. Okay. The case of the scalar multiplication, you can also ask the same question, which one you should do first, scalar multiplication first, or or transpose first? Well, it doesn't matter again in this particular case. Okay, so that's easier to do. What about trace, which we left a little bit before this? Okay, because I wanted to introduce transpose first. Now, the case of trace, you'll see that using the index notation again will help you a lot. Okay, for example, I have trace of A plus B, so that corresponds to what? That corresponds to the sum of A plus B, the ith element, which is the diagonal element. So the diagonal elements of A plus B is equals to the addition of the diagonal elements of A plus with the diagonal elements of B. And then you can separate the sum, so that corresponds to the trace of A, this trace of A, and this trace of B. So you can actually do that. Okay. So again, the scalar multiplication is much simpler, so I don't want to go through too much. Okay, so that looks good. So you have addition, scalar multiplication, and then transpose, and then you have your trace for the case of a square matrix. Okay. So what other operations that one can introduce? So over here it becomes a bit more interesting. We want to introduce, for example, multiplication. If it's vectors, you remember vectors have two types of product. One is called scalar product, right? The other one is called the cross product. Now, generally, the matrix, what kind of product do we actually have? Well, in this particular case, there are many different ways of introducing products, but the product that we want to introduce over here is common to what we call I think it's called a matrix product. Okay. There's another one called the Kronecker product. The matrix product is just saying what do you do in the case of a two matrix over here. You take the row, multiply with the column, right? I think everyone has done this before. Why is it has to be that? Can anyone answer me? Why does it have to be row times a column? I want you to think a little bit. Is there a particular reason why you want to do that? Do you understand matrix product? Why it happens to be that way? Nobody? Any guess? Why can't I have a matrix product, for example, that does something like this? I say, let's take two square matrix here. Okay. Alpha, beta, gamma, delta times A, B, C, D. Why can I do this that way? Alpha A, beta B, gamma C, delta D. Can anyone tell me what is the problem of that? Anyone? Do you think you can make a product of two matrices in this way or not? Everyone seems to be very quiet today. Maybe it's after lunch. Does it make sense to have this product? Why? When you say no, that means you already have some kind of reasoning uh, saying that this doesn't work. So why? See, sometimes this is the thing that I wanted you to be aware of. Some of the things that you assume, there is no real natural way of presenting a matrix product. Excuse me. There's no natural way of introducing matrix product. No, until you get so used to it, you think that's the only way. Actually, you can do it many different ways. But no, I'm just letting you understand why that should not work in this particular case, because you want to maintain one of the things that, for example, you want to maintain, for example, let's suppose I have, let's call this whole thing A, and let's call this B. So you have a product defined this way, and then you also have addition. Okay, so when you sort of combine these two operations, you need it to behave in a certain way. And when you do this, this might not work that way. Of course, if you don't care, if you just have your product, you can actually define this way you want to. But there are things that you need to introduce when you have two different operations into the object. So that's why in this particular case, you don't want to do it this way. Okay. So there are properties. When you make combinations of them, you want it to be compatible in some way. Okay. So the matrix product that you see over here, for example, has to be compatible in this particular way. It's called conformable. So if it's m by n over here, then the matrix that sort of post multiply it in some sense, because it's on the right, post multiplied it has to be whatever rank this, or whatever, what do you call this, this is called the number of columns. Okay, I can't remember the name for it. Number of columns over here should appear also in the number of rows over here, so that when you combine these two, it becomes an M by P matrix. Okay. Now it doesn't have to be that way, but that is what we need in this particular case, especially when you want to introduce other operations together with matrix multiplication. Now I want you to do an exercise. Okay, when you do matrix multiplication that way, for example, can I do this? Okay, does this becomes A, B, C plus A, D, E? Try to convince yourself that this is the same as that. So in other words, over here, it doesn't really matter if you do the addition for the multiplication for these two things first, and then multiply with another addition. I don't know. That's okay. I'm doing a lot of different things away. I'm composing addition as well as matrix multiplication, but you also have the addition on this thing. There is another property that I should introduce first. Before I do that, I should introduce that A, B, C. Okay, you know how to multiply two matrices, but how do you multiply three matrices? I can multiply any two matrices first. Okay, this is the same as multiplying matrices in this way. So then you can always write A, B, C without the bracket because they are equivalent. Okay, so I actually use this inside here as well. Okay, so again, there are structures that seems to be natural when you combine two types of operations in this way, and the multiplication that you define in this way must be what we call of conformal type for both matrices. Okay, and then you'll be able to mix things around. Right. Once you have done that, for example, that in the case of let me see. Okay, in the case of, let's say, AB is an M by P matrix, which is resultant from, I think it's over here. Okay, so here is M by N times N by P, right? So you get M by P matrix, but you can also do the reverse multiplication, B times A. So that will be what? N by P multiplied by okay, I need your M to be P as well. Let me see. What do I do over here? The result matrix. Okay, I would need over here, in order for me to be able to do this, I would need your matrix A to be P by N matrix. Is that right? B is only possible if B is an M by M matrix. Here is, yeah, okay. So it's the same statement. So in other words, your A, if I use this notation here, N by P, then A will have to be a P by M in general. So let me see. So here is M by P. So this will be a N by M. So you multiply these two together, it's N by M. So okay, the point I want to do this is to show that multiplication, when you define even in this particular way, they are not commutative. Commutative means like numbers, for example. You have A times B equals to B times A. So this is commutative. This is what we call your product is actually commutative for numbers in general, but for matrices they are not. Okay, so in this way, generally when you have two matrices in this way, one can actually try to find how the commutativity fails, how this property fails, and what is defined here is a commutator. Okay, the commutator in a way measures how the commutativity fails, how this identity fails. Okay, so you define a commutator of A and B to be A times B minus B times A. Okay, and that will tell you, okay, how much the matrices differ from the, say, the property of a number, for example. Okay. So, and why is this actually important? Later on, when we have you done quantum mechanics yet? I should ask you a simple question like this, where you can answer yes or no. Have you done quantum mechanics? Not yet. Okay. Commutator are one of those things that appears inside quantum mechanics. So in quantum mechanics, sorry, where was I? In quantum mechanics, you can define certain objects by matrices, and then you find that, okay, this matrices doesn't obey this commutative kind of thing, relation between products. Okay, then you define what we call a commutator. So in this particular case, one of the important ones are, if you have heard about Heisenberg uncertainty principle. I think in modern physics they should teach you that. Heisenberg uncertainty principle. Have you learned that? Not yet also. Okay. Have you done modern physics? Or there's no such thing for your batch? Can't remember now. Everything has changed. Do you have modern physics? Huh? Currently taking it. Okay. I'm pretty sure you have done matric or STPM, right? Otherwise, you won't be in the university. So you probably have heard about Heisenberg uncertainty principle. Please say yes if you've done so, because I really want to make this a bit more interesting than just introducing just matrices, which you have seen those before. Okay, so over here you have something like the uncertainty of position multiplied with uncertainty of momentum is always greater than equals to some number, which is this is actually called the reduced Planck constant. Okay. And you can trace this all back to the fact that the commutator of position and momenta in quantum mechanics is not equals to 0. Okay, so you can trace that this thing that you learn probably in modern physics, or probably I think you should be learning this in even STPM or pre-university level. Okay, to say that, okay, in quantum mechanics where your things like electrons or atoms, you are not able to define precisely both position and momentum. There will always be some uncertainty in one of them. In such a way, they obey this uncertainty principle. Okay, so these are why this actually comes up. It comes from the property which is related to the product of matrices in that way. Okay, I hope it makes sense to you, but okay, I'm just trying to make it how it connects with certain ideas in physics. So the matrices over here do not commute in terms of the product. Here are some examples, which is probably not so interesting to you, but because you can always do this easily. So here you have a 1 by 3 matrix multiplied by a 3 by 1 matrix, right? So the resultant here will be a 1 by 1 matrix. Some delay there. But if you swap them around, okay, I'll have a 3 by 1 matrix with a 1 by 3 matrix. I'm pretty sure you have done this before. No, you take a row matrix multiplied by a column matrix, and you get a number. Okay, but now here you have a column matrix multiplied with a row matrix, and what you're supposed to have is actually a 3 by 3 matrix. Okay, so some of these things can actually probably you have not used it too much, but it appears in areas of physics like quantum mechanics. Okay, now you have done addition, scalar multiplication, transpose, trace, and then you introduce product, matrix product. Now you can also make combinations of trace and matrix product and see what you have. Okay, so here if I were to take the matrix that we defined above, trace Mn is just a 1 by 1 matrix, and that is the only diagonal element. It's just one single element. So 1 by 1 matrix. Okay, so that is already a diagonal element. Okay, and it's equals to AD plus BE plus CF. But if you take the n times m, it's a 3 by 3 matrix. And a 3 by 3 matrix, if you take the diagonal element, what are they? It's DA, EB, FC. And remember, these are numbers. Okay, D is a number, A is a number, E is a number, B is a number, F is a number, C is a number. And you compare the answer there. Okay, I have that, right? And DA is actually equals to AD, EB is actually equals to BE. Oops, I don't want that. And then CF is equals to FC. So what we have established here is one property called the cyclicity of your trace. Okay, the trace of two matrices, the product of two matrices, if you swap them around in a cyclic manner, no, it's always give you the same answer. Okay, so in general, what you have something like this. Here I'm doing this in terms of the indices. Okay, so how do you okay, here I'm doing the adding up diagonal elements I here, but how do you get I element from a matrix A multiplied matrix B? Well, one introduce another sum over here where one needs this J, which is giving you the column, must multiply with the row of this matrix. So I get Aij and then B times Bji. Okay, so what happens over there, this index is the same with this index. Okay, so what happens there also, you can swap this around. This Aij is a number. Why is it not working properly here? This Aij is just the ijth element, right? So it's a number. So I can swap that around. So Aij, Bji, both are just numbers. I can swap them around, becomes Bji, Aij. Okay? But what happens to the sum? Here I'm summing J first, and then sum I second time. Okay? I could swap these two sums, then I'll get this. I'll do I sum first, okay, and then the J sum to be the second sum. And then this is precisely the matrix B multiplied by matrix A. Okay, and because you're taking the trace, then you really get your matrix BA sum over the diagonal elements. So here you actually prove this in a much more general context, that trace of AB equals to trace of BA. And you can extend this into even product of many matrices Here is the case of a product of three matrices. Trace of ABC equals to trace BCA equals to trace CAB, and I leave you as an exercise over here. Prove this using indices like over here. Okay, and you are not just limited to product of three matrices. You can do a cyclic identity again for any number of matrices. For example, over here I have A1 to A1, A2 until AM. So I'll just do a cyclic thing. So this one goes to the back and I get that. And then this one goes to the back, I get A3 multiplied by A4 until AM multiplied by A1 until A2. Okay, so you get that cyclic sort of operation within the product of the matrices, and the trace are just the same. Okay, so okay, some of these things are not actually done in this way in BOAS, because BOAS tend to be a bit more less theoretical than what I do here. Here I'm trying to introduce here a much more general idea than what's been done in the book, I suppose. So okay, here I want to introduce another object called the Kronecker delta. Has anyone heard about Kronecker delta before? Again, yes or no? Why? So okay, Kronecker delta is just a constant. Okay, a constant that depends on the index. Okay, so if the index is the same, then you get a 1. If the index is not the same, then you get a 0. I tell you where one particular place where you use this. Remember the dot product of two vectors. So if I define the vector to be just a single index object as Vi, and then the other vector here will be, say, Wj. In order to implement v dot w, I need a delta ij here, and I need a sum over I and j, 1, 2, 3. So let me just do this in a little bit more detail to show that, okay, there are certain structures inside your things in your linear algebra that makes use of this structure unknowingly. So one of this is essentially your Kronecker delta. So if I just do this sum over I and j, I will do, let me do the, okay, let me do j first. So I do Vi delta I, so I need a sum over I after that. Vi delta I, and then I have 1 W1 plus, new bracket here, Vi delta I2 W2, and then Vi delta I3 W3. Okay, so that is the sum over j here. Then I do the sum over I, then I will have V1 delta 1 W1, V2 delta 2 W2, W1, oops, I need to go up a little bit. Oops. Give me space there, so I'll have here V1 delta 11 W1 plus V2 delta 21 W1 plus V3 delta 31 W1, and I just go a little bit on the second line. Here I need I equals to 2, so I have V2 delta 21 W1, and then proceed with V2. Where am I? I'm getting confused now. I here 1, 2, 3. This is with respect to that. So I need the same thing over here. Sorry. Okay. Should have done that. Okay. So I should have I equals to 1 again over here. So V1 delta 1, 2 W2 plus V2 delta 2 to W2, and so on and so forth. Okay, until V3 delta 3 W3. Okay, now this looks like, why am I introducing all this complicated stuff? You know that this is already what? It's V1 W1 plus V2 W2 plus V3 W3, right? From your ordinary dot product. But I'm just trying to say you that this actually is inherent in this dot product in this way. So if you look at all the terms over here, this one gives you a 1, but this one gives you 0, this gives you 0, 0, this gives you 1. So only the terms with the same index, okay, because if it's the same index equals to 1, different index equals 0. So the answer that you get is precisely this answer. And that happens for the case of a dot product. For the matrices, the Kronecker delta here implements the trace. Okay? So these are things that no, if you write it out, then you get your definition of a trace. So there are structures hidden underneath some operations that you just normally use it without thinking. Okay, so those are things one should know about matrices in general. When I use all these indices, okay, when are the indices useful? The indices, the so-called index notation, are useful when you want to prove general cases. So one of the things that we have shown just now is like the product and the addition sort of operates equally. In that sense, then you will see that okay, the index notation does it in one statement without going through one by one using a particular number. Okay, so if you have matrices given by numbers, then you can do it without going to the index notation. Okay, so the index notation are just useful to consider when you have general statements, general cases. Without so your matrices are not really explicitly given, then you use index notation. And this is the same thing happens to vectors as well. So if you do vectors like V cross W, for example, the cross product, it'll be easier if you know your V in terms of numbers, the components, and W in terms of numbers, okay, or the components. But if you want to do it generally, this is going to be difficult. Okay, so that's what I'm saying. Okay, so in case of the general case, then you probably would need what we call the index notation. Okay, I think I'm going to take a break for a few minutes. Is that all right? Or you like to continue or break? Okay, so we'll take a break for say 3 to 5 minutes. Okay. Okay, I hope everyone is back. Very quiet. So okay, any case I'm going to start anyway, so I'll start now by just telling you, okay, don't be afraid or don't get turned off by all those slightly abstract idea that I just introduced to you just now. You could have done it in a way that Boas did. So Boas did it mostly through numerical examples. Okay, for example, over here, now it does it by using numbers inside your matrix, and then you know how to handle matrix with numbers in. I'm just telling you some of the things that been done there. You can actually generalize it in a much more abstract way. So hopefully that doesn't turn you off, or if it does, then you just follow Boas' way of doing things, but some of it may appear mysterious why it works that way. Okay, so I'm trying to just getting rid of that mysterious aspects of algebra in a way. Okay, let me go back to where we are. So one of the things that was actually done by Bose almost immediately when it introduced matrices over here, going up, is to use matrices as a way of solving what we call linear equations. Okay, that's another thing that is also part of the linear algebra thing. Okay, but over here I'm doing it not in that what you call not in that order. What I did was just now was to introduce matrices in a much more general way, and then introduce the idea of solving linear equations as part of the properties of matrices that we have just introduced. Okay, so here is essentially the next thing that we do in this particular lecture is to look at linear equations. Again, you can see that, okay, there are one thing being fixed in this set of linear equations. What are the fixed things over here? So you have you have several equations over here, but one of the things that can be fixed is actually here, your x1 here, x2, xn, and they all appear on each of these equations. So when that happens, you know that, okay, this comes from a much more simpler equation than what you have seen in this array of equations. I can rewrite this thing as a product of two matrices. And of course you know this, okay? So when you do this, you take the row multiplied by the column. Okay, so the first row multiplied with this column give you the first equation. Okay, so you get m11, m12, m1n there. So you get the first equation, and then you take the second row multiplied with the column, then you get the second equation, and so on and so forth. So in other words, solving simultaneous linear equations like this amounts to solving a matrix equation like this. Okay, so if you are able to use the structure of matrices, okay, then I'll be able to write this thing as matrix M times matrix X equals matrix C. Okay, and if you have done matrices before, the solution to this will be easy because I just need to find the inverse of M. So it denoted as M inverse that way. So you multiply with mx equals to C, then this would be equals to, let me write it down here. I get M inverse mx equals to M inverse C. M inverse M will give you the identity matrix. Okay, and identity matrix times X will just be equals to X. So that gives you X equals to M inverse C. So you can see that, okay, this is much easier than trying to do the solving of linear equations in the ordinary algebraic way. But of course, there are things being assumed here. One of the things where this would be actually not working very well is when you have an equation something where C equals 0. And if you do that, then essentially the only solution that you get is going to be X equals 0. Okay, so there are things that one can do in that sense, in the matrix sense that I've just mentioned over here, but no, for other cases you need to do it differently. Okay, so you need to be able to see all these possibilities in this manner. Okay, another way that people treat what you call set of linear equations, solving set of linear equations, is to use what they call an augmented matrix. Okay, so what it does over here is to say that I don't care too much about this X, but I just need to know what are the properties of this M over here, the matrix that multiplies the X, and what are the properties of this C over here. And what I'll do, I have this new matrix constructed of that M and that C only. So I don't care what happens over here. In the end, no, you get the solutions that you want. Okay, so what is this thing that's being needed? Let's take the simplest case first, which the simplest non-trivial case. So the simplest non-trivial case is the case of two variables with two equations in this way. And this is still general because I'm not putting numbers for your A, B, C, and D here, and your M and N here. No, we keep it as general as possible. Okay, so what do you do in this particular case? If you really want to solve for X and Y, the best thing is to do some elimination technique. Okay, so how to do this? For example, I see over here I want to eliminate Y, for example. So what do? If I multiply the whole equation by D, I get BD here times Y. And then if I multiply this equation by B, the whole equation, then I get DB here, or BD again. But the two they are just numbers, so they are commutative. So I'll get the same coefficient multiplying Y on top and bottom. So if I have that, then I can just subtract this away. Okay, subtract this equation by that equation. Then I'll be removing the dependence on Y. So I'll get your equation that involve only the variable X. And then essentially, once you do that, I'll get the solution for X. dm minus bn over ad minus bc. Okay, and similarly, you can do for the other one. Okay, so the top one you solve for X. Second one you solve for Y. So how do you eliminate x in this particular case. So you look at what is multiplying x on both equations. Over here is a, so I multiply this by c, and over here is c, then I multiply it by a, and then subtract again, then I get this equation, and again I'll be able to solve it. The y equals to cm minus an over bc minus ad. Now it'd be interesting to see that I get the same denominator. Well, I mean, one is negative of each other, okay? And that number that you get from AD minus BC actually comes from, I didn't do it over here, actually comes from what? If I think of this equation as a matrix equation, then I will have what? A, B, C, D times X and Y equals to M and N. If I take the determinant, I believe you have done determinant before, this is AD minus BC, which is precisely the numbers that you get over here, well, plus or minus, okay? And that is related to another technique, which is called Kramer's rule, okay? So we have not really introduced determinant as yet. So that's why, no, I'm trying to do this step by step. Determinant is much more complicated, okay? Because determinant is a nonlinear operation, okay? So I'm going to do that later after we understand properly what are we doing in this particular easy case first, okay? So in other words, we can do this algebraically by eliminating variables, okay, and we can get the solution. But what is involved inside the inside this elimination techniques? Well, the elimination techniques are involving things like this. You add a multiple of one row to another, which is, no, you take the difference between the two rows that we have actually seen. You multiply one row by a constant that we have seen multiplying, say, for example, over here, you multiply by C over here, okay? And the other one is to swap rows if you want to, okay? So these are the elementary steps, elementary operations. Why is it elementary? Because you only use what? You only use addition, scalar multiplication, which have introduced much earlier when we introduced matrices. These are the two basic operations, okay? The swapping is of course a slightly different thing, but the basic operations, the mathematical operations are essentially those two. Okay, so what we want to say is, okay, if we have a much complicated case of simultaneous linear equations, then maybe we can just simply adopt this kind of elimination techniques using these algebraic operations. Okay, so this is the essential claim. We want to do what we call the elementary row reduction steps. Okay, and where do we apply to that? We apply it to the augmented matrix, because what we are concerned is mostly the structure of matrices that multiply the variable and the answers on the right hand side, the numbers that appears on the right hand side. Okay, so we use elementary row reduction to the augmented matrix to solve the linear equations. Okay, and to do this theoretically is a bit there's a way to do this theoretically, but I would rather demonstrate that because it will involve other things like things like eigenvalues and things like that, which I will introduce much later on rather than now. So let's do this for a numerical case, meaning you have a numerical number here, okay? So multiplying the variable x, y, z, and then here also you have numbers, okay? So first thing that we will do is to create the augmented matrix. So you look at the numbers that multiplies variable x, that will come as the first column. The numbers that multiply y, that will come as second column. The numbers that multiply z, that will take up the third column. And then the fourth column, which sort of appends to this original matrix that multiply x, y, z, is the right hand side numbers. Okay, so all we need to do is now to apply this elementary row reduction technique in a way that, okay, let me just go through all those steps over here, in a way that what you want is to get the identity matrix. You do all the row reduction techniques to the matrix that you see, reduce it to the case of the identity matrix, and then the identity matrix multiply with the x, y, z, okay, will be just x, y, z, okay. So these two will just give you x, y, z, and this will give you the answer, the solutions. Okay, so let's go step by step. So what are the row reduction technique that you need to do in this particular case? First, what we do is, let's see if I can interchange rows, for example, to make that, okay, remember that I need something like this in the end, 1, not 1, not 1, and then you have your augmented thing, okay. So I need this, so I need a 1 over here. But I already have a 1, but it's in the third row. So I can just swap it, because swapping is an allowed operation. Okay, it's just redefining your number of rows, redefining the label of rows and columns. Okay, so I just have that swap between row 3 and row 1. So I get the resultant matrix. And then I start to do, okay, what's next to do is to see that in order for me to get this shape, okay, I need a 0 here, I need a 0 here. So I have a 3 here, I have a 2 here. Okay, so in order for me to get a 0, by adding these two columns, is like before, like, no, you multiply this by 2, and we multiply this by 3, okay, and then you take the difference between the two. Then of course this becomes 0. Okay, so that's what we did over here. The step 2 is to perform this arithmetic operation in a way, because you just do a multiplication, scalar multiplication here, addition here, which is subtraction, okay, and then do the same thing for the third row, and I'm reduced to this matrix. So I've already got that 0 here and 0 here, and then continue. Now remember, I need a 1 here, I need a 0 here, I need a 0 here, I need 1 here, for example. Okay, so you continue to do all this row reduction exercise until you get to the point of reducing everything. Here is almost done because I have zeros over here and 1 along the diagonal here, but I still have some non-zero here, so I'll reduce that, okay, and finally we get the answer over here. Okay, and remember that this part of the matrix will multiply your x, y, z, and this part of the matrix, okay, is your solutions. Okay, so in other words, we have done this using the augmented matrix finally to get the solution. Okay. Now, this one I already mentioned before is to look at the whole thing as a matrix operation. So I just need to know how to do inverse matrix, which I have not actually taught you how to do it. That's it. Okay. Given a matrix M, can you actually find your inverse matrix? Let me check. I'm just afraid I'm get disconnected. Okay. What would be how to define the inverse matrix? I'm not sure whether I've done this here. Well, okay. Actually, I've done, but not using the determinant technique. So I'm using the matrix elementary row reduction to find the inverse. Okay. So what's the claim here? The claim here is to if you do the same row reduction matrix, okay, so I'm now appending matrix M, here's matrix M, but I appending with a different matrix, which is not your right hand side, but now it's an identity matrix. So I do row reduction techniques to both M and I appended by I here to all these numbers, so to speak. Okay, perform row reduction techniques until your M goes to I, and if this happens, okay, this has now become the identity matrix now, this will turn to M inverse. So let's look at the example that we did earlier. So we have this M matrix. Okay, you just check the example that we had before, and then I append this with the identity matrix. Okay, do the same row reductions. Okay, I'm swapping here. This row goes up, then this row goes up there, and then you do all the different techniques. I do not want to go into the details, but you can see this will evolve just like before. Okay, until it goes down to this identity matrix over here, and then this one becomes used to be the identity matrix here. Now this becomes a M inverse. Okay, and that will do the job. Okay, so if you want to be sure, you can just check your M inverse, the new M inverse that you have actually obtained from row reduction technique, multiply with M, that should give you the identity matrix, and in this case it works. So what's the use of this? Well, remember we had this before, this equation before, so I just multiply M inverse on the whole equation, then I should be getting your solution here, which is precisely this one. Okay, so that row reduction techniques, why this is so useful, because when you implement this inside computers, addition and scalar multiplication is a very elementary thing to do for computers. If you try to do, say, working out the determinant or something much complicated than that, then the computers find it difficult to do. But row operations like this, like addition of two rows together, or swapping rows, or multiplying one row with number, those are easy things that can be done on the computer. So that's why this is actually important. Okay. So here is another example. this example is an example where things can fail. Okay, here you have your augmented matrix. You see this 1, 2, 1, minus 1, minus 3, minus 2 here, and then 3, 6, 3. So what happens over here, if you do row reduction, you come to the point where, okay, I try to do getting all the zeros here, but I find the last thing to that happens over here, this third row, which is supposed to be the third row of the matrix, okay, becomes all zeros. Okay, now if you look at this equation itself, what does it mean? It means 0 times z is actually 0 times x plus 0 times y plus 0 times z equals to 1. But that's impossible because 0 is not equal to 1. So in other words, this set of solutions has no solutions. Okay, so no solutions to this because of this problem. Okay, another possibility is to have infinitely many solutions. Okay, so here is another place where it also can fail, not having a particular solution, but instead you have many different solutions. Okay, so here's again a set of linear equations over here. Okay, and what happens there is if you try to put it as an augmented matrix over here, then finally you come to the point where you do a row reduction and you find that these two are the same. And once you have that thing, you will not be able to get, well, you can do the row reduction further, but you get all these zeros in the end. Okay, so what happens over there is like 0 times x plus 0 times y plus 0 times z equals 0. So in other words, I may be able to get some what you call, sorry, I don't want to do that. I'm doing I may be able to do further row reduction for the upper part of the matrix, but I'll find that. So in other words, one of the variables will go to be unsolved. In fact, what do you have over here? This part of the matrix will give you this equation and this equation, for which you have your x and y being written in terms of z in that way. So there is a one undetermined variable. So in that case, I can have z to be equals to anything, or in that case, that will say that, okay, I can have infinitely many solutions given the value of z, right? As long as they obey these two equations. Okay, so there are two things that one needs to look carefully, and how do you know a particular set of linear equations is going to be giving you a unique solution, or no solutions, or infinitely many solutions? One is to look at the rank of the matrix M and the rank of the augmented matrix A. Okay, so what is the rank? The rank is the number of non-zero rows after doing the row reduction process. Okay, if you can reduce it to no, some of the rows are all zeros, then the remaining two rows, or the remaining rows, will be the rank of the matrix. Okay, so one can look at both the rank of this matrix M and the augmented matrix A. If the rank M is less than the rank of A, then what you have is your equations are actually inconsistent. I do not know how to spell inconsistent. Okay, so in that particular case, then there will be no solutions. The one that we had before, your rank of M is 2 and your rank of A is 3. And you can check this later on. Okay, if you have the rank of M equals to the rank of A, and this rank of M and A is equal to the number of unknowns, meaning x, y, z, for example, is 3. Okay, so if there are more variables, then you have more, your number n will be bigger than 3. Then if that actually happens, then you have a unique solution. So the case that we have seen earlier was rank M equals to 3 and rank A equals to 3. Now we have remaining one case where you have infinite solutions. Well, the infinite solution case, you have your rank M and equals to the rank of A, but it gives you a number here which is less than the number of the variables. So in this particular case, then you have your infinite solutions case. So in other words, you can always get the type of solutions that you can have by looking at the rank of the matrices involved. Okay. Do I want to do this now or should I leave this later on? Okay, maybe I'll just introduce it. Okay, earlier on we had this set of linear equations involving only two variables, x and y. Okay, so I can rewrite this as mx equals to c like before, and then I will just need to find out what m inverse is. Then I should be able to see your solution, right? But let's see the details, what's been involved in this particular case. You see this, I think I've mentioned this before. Okay, you have this factor on the denominator which corresponds to the determinant of this m. What is the determinant of this m? Is you multiply this together minus that. Okay, so this becomes AD minus B. So that is called the determinant for the 2 by 2 matrix. For higher dimensional matrix, then we need to do a bit more work than this. Okay, but you see that, okay, one of the things immediately that we can actually see, in order for us to get a unique solution, then your determinant of m cannot be equal to 0. If it's equal to 0, then you have 1 divided by 0 here. Okay, so in other words, that is already one indication of no. Okay, in order to have a unique solution, then I need your determinant of m is not equal to 0, and this is related to the existence of this inverse matrix. In fact, for 2 by 2 matrix, I hope you have done this before somehow. It's equals by one determinant m, and then you swap the two the two entries here, the a, and this gets a minus sign and this gets a minus sign. Have you done this right? Is this familiar to you?
Yes, Doctor.
Okay, great. So at least you have done determinant of 2 by 2 matrix. Have you done determinant of a higher order matrix like 3 by 3? Yes or no, please? 3 by 3 matrix, determinant. Nobody wants to answer? I assume it's yes. So you know how to find the determinant of a 3 by 3 matrix. Yes. Oh, great. So that's okay. I thought that you have not done it. So then it will be easier then. Right. Okay. So in other words, one of the things that's going to be helpful is to be able to define determinant. Okay. So I think in the next lecture or so, I'm not going to go for the whole 2 hours because that would take too much processing time of the video. We will learn how to do determinant of a n by n matrix. Okay, and the procedure is called the Laplace expansion. And there is another procedure which is using the index notation. Let's see whether why is it not coming out? Actually it's related, the Laplace expansion and the index notation thing is related to each other. Okay, so we'll do that probably in the next lecture or so. But let me remind you about your first test will be next week, Monday. I will be giving you the assignment today sometime in the evening. And can I have you, let's say today is what? Let's clear this. So assignment 1 today, only I just need to type it out essentially. Assignment given, oh come on, looks horrible. Ah dear. Doing clear. Let's discuss when is it due. So I have to write slowly so you can actually capture my writing. Assignment made available today. Today is 8/11/2021. Can you hand it in by Saturday? Saturday, say 12 noon. Delay here. I have to write very slowly. Saturday, when is Saturday? Saturday is Saturday is 13. And then solution I will give on the following day. And then your test will be on Monday during class time. Is this okay? Okay, great. So I'll do that. So I'm just typing it out. By tonight at least I think it should be done. Okay, it's just I need to select the questions from the book, and then select in such a way that you are able to practice each type of questions, so that your knowledge is up to what we need. Okay, and then hand in the solutions, and I want you to do this in a group, in a pair. I did mention this before. When you do it in a pair, the intent here is probably you share the workload a little bit. No, you do not want to do all the problems by yourself, so you share the workload between your partner, and if possible, no, do this fairly, so your partner will have the same chance of understanding the problem. Okay, and then you state, no, if you do it equally, okay, I did 50% of this set of problems, and the other partner do 50%. Okay, if you can actually do that. Okay, so so I will create a folder for you to submit by a representative of your pair. Okay, and hopefully, no, you get some practice from there. Okay, that's it for today. So I will take your attendance now. My computer's slowing down. Oh, come on. Yeah, good. Okay, I think that's it. So I've downloaded the attendance. So if there are any further questions now regarding the test or assignment, or otherwise we'll say goodbye at this stage. Any questions? Yes. Yeah.
The assignment will be hand in by Saturday by 12 p.m., right? 12 p.m.
Yeah, 12 p.m., not 12 a.m.
Oh, okay. 12 at noon.
Okay. All right. Okay. Is that the only question? Okay. Then we should say goodbye. I don't want to make this recording too long. Okay. Bye, everyone.
Doctor. Bye, doctor. Thank you, doctor.
Thank you, Doctor.
Thank you, doctor.